Hello, everybody. My name is Madalina. I'm from Romania. I'm an engineer in computer science, and I did a PhD in my 30s. I have been working for 10 years in machine learning, and currently I am heading the data science department at Kiwi.com. Who had to work on a project requiring you to learn fast an intimidatingly complicated topic, while most available tutorials refer to older methods and very little of the challenges that you are actually going to face? I did. And this is why I'm here today, to give you a fast track into the fascinating world of anomaly detection. Thanks. So, we will check what anomaly detection is, what challenges you are expected to encounter, how you can mitigate them, what data sets you can leverage to benchmark your results, what is the correct way to evaluate these results, what libraries can get you started as soon as possible. I also prepared a GitHub repo that is going to exemplify all the techniques I will discuss today. However, the time is limited, and in my attempt to provide a 360 degrees up-to-date overview of the field, the content cannot be complete. It will reflect my personal preferences. However, it is a starting point, and I hope it will also help you save a lot of time. Without any further ado, what is anomaly detection? It is the identification of rare events that deviate from our expectation of normal data, or inliers. And it comes in two flavors. Outlier detection, when we focus on abnormal samples that already contaminate the training set, and novelty, when we refer to new and unseen patterns in the data that didn't already make it in the training set that we gathered. Anomaly detection is a key ingredient to observability. Observability is a paradigm understanding a system's internal state through the usage of logs, metrics, and traces. However, it goes deeper than monitoring because it attempts to understand the why behind what is being observed, to anticipate problems, and thus to move from reactive to proactive. And this is achieved through different techniques, among which anomaly detection, drift detection, root cause analysis. These techniques help us build models that are reliable and have a reduced downtime. However, drift detection and anomaly detection are close topics, and they can be easily confused. To clarify, given our expectation of normal data or of inliers, anomalies refer to individual points that deviate from the normal data, while drift refers to a shift in the overall distribution of the data over time. So they are different phenomena with different detection methods. If you're interested in drift, this is not a topic of my presentation, but I suggest checking out the library Alibi Detect. Why should you care about anomaly detection? Because it is ubiquitous. It is relevant in all industries and across all types of data. If you work with tabular data, for example, the omnipresent scenario is fraud detection or inventory management. If you work with images in surveillance, we have intrusion detection. In life sciences, disease detection. On time series data, predictive maintenance, the analysis of financial markets, network security, healthcare monitoring, and many more. The remaining content of my presentation will focus on the analysis of time series data. However, most of the methods that I will present today can also generalize to the other types of data. How can we solve anomaly detection? There are three big settings. First, if you are extremely lucky and you have only annotated data. It's the supervised setting, in which you can train a binary classifier for normal data versus anomalous data. But most likely, you will have only partially labeled data together with a large quantity of unlabeled data. This is the semi-supervised setting. Or even more likely, you will lack any annotation at all. This is the unsupervised setting, which is also the most technically difficult one and the focus of my presentation. So from all different scenarios and experimental settings, my presentation will focus on the unsupervised anomaly detection of multivariate time series data. I know this is a mouthful, so let's go through each of these individual terms, explain what they mean, check what problems or opportunities they bring, and then I will also explain why I chose this particular setting. As I mentioned, in the industry, it's rare to get annotated data. Most data is unlabeled. And when we do have it, it can be of poor quality. So fixing anomaly detection in the unsupervised setting is the most versatile and the case that generalizes easiest. However, in the absence of ground truth data, it can be difficult to validate the results and also to find the appropriate threshold that would discriminate from anomalous data and normal data. More on how to address these challenges in a minute. The anomaly detection part is expected to bring the computational challenge of extreme class imbalance, because anomalies are rare events. Additionally, it can also be challenging to discriminate anomalies from the expected noise in the data. The time series part refers to the fact that real data, both normal data and anomalies, evolve over time. And if we look at it from the perspective of this temporal evolution, we can identify different types of anomalies using different detection methods. For example, on a point level, we can have global anomalies or contextual, but they can also be related to a recurrent pattern. This pattern can be seasonal, related to the trend, or even more generally, to any kind of shapelet. And the multivariate part refers to the fact that we are analyzing more than one time series at a given moment in time. We have multiple time series, and the values of these time series relate to one another. And this brings the challenge known as the curse of dimensionality, because we have multiple time series, each of them having a potentially significant dimensionality. So the remaining part of my presentation will focus on the following setting. You are given n time series of an arbitrary length and no further information. Your mission is to identify when at least one of these time series exhibits anomalous behavior, either by itself or in relation to the other given time series. Why did I choose this particular subscope? Because it's the one that contains the fewest available tutorials or blogs. It can be addressed through a variety of ways. It's the one that is closest to what you will experience in the industry, most likely in fraud detection, in predictive maintenance. It's highly versatile and generalizable. If you have an unsupervised solution, you can always leverage it in combination with the other semi-supervised and supervised settings. And it's also the one that brings the most difficult technical challenges. Before jumping into Python methods, let's do a quick refresh of the theory behind anomaly detection algorithms. Different surveys, including the one cited here, group the approaches into 5 categories. First, even if we are in the unsupervised setting, we want to learn a binary decision boundary on our data. So we want to split samples into anomalies and normal data. And in doing so, most likely, we will need to provide extra information. For example, an expected rate of contamination in your data set. It's possible that in practice, you don't know this information, and its value is going to tremendously affect the result of the algorithm. The methods in this category work best with tabular data. Like most of the research in anomaly detection is focused mostly on tabular data. If you work with time series data, you can still handle it. For example, instead of considering a sample, a snapshot at a given moment in time, you can look at a rolling window around that sample. The handbook methods that we learn at school are isolation forest, one-class support vector machines. In the second approach, we want to relax the condition of binary classification to a probability. So we want to predict the probability for the density function of normal data. Similarly, these methods work best with tabular data. If you have other kinds of data, you can still transform it in such a shape. The outstanding methods here are local outlier factor or clustering. For example, you can cluster your data set using density-based clustering or Gaussian mixture model, and all the points that will fall outside the identified clusters would be considered anomalies. In the third approach, we look at the distance between a sample and all its neighbors, and we want to determine a threshold for the distance beyond which a sample is considered far enough to be an anomaly. For example, if we work with time series data, a very common method is the Bollinger Bands. In this case, we want to look at the distance between a sample and, for example, the rolling mean average or any other metric. If you want to compute distances between time series, you can check dynamic time warping as a distance metric. Finally, in reconstruction, we want to train a model that is able to predict the current state of the data or to reconstruct it. And here, the intuition is that when we start getting large reconstruction errors, this signals the presence of anomalies. The typical methods can be simple, like PCA or Kellner PCA, but can also be methods that leverage neural networks, for example, autoencoders or generative adversarial neural networks. And in the final approach, if before we were trying to predict the present state of the data, we want to predict now the future. We want to predict how the data is going to evolve if it is coming from the normal distribution that we already observed. And similarly, when we start getting errors, this means that anomalies start occurring. The typical methods in this case can be autoregressive models like ARIMA, as well as methods that are based on recurrent neural networks or, more recently, transformers. You might have noticed that across all these 5 categories of approaches, we have the recurrent topic of thresholding. How do we find a distance or a contamination rate that would split anomalies from normal data? In some cases, you can leverage business knowledge in order to set the right threshold. But very often, this information is not known in advance. And in that case, you can check non-parametric dynamic thresholding, which is a set of unsupervised methods that leverage different statistical tests that avoid making assumptions on the data distribution. These thresholds can also adjust over time, can also evolve over time. If this is of interest to you, I suggest checking out the library called PyThresh. It's amazing. It comes with 30 algorithms for non-parametric dynamic thresholding. Okay, now let's get our hands dirty. We checked the algorithms, and we want to apply them on some data sets. A very good starting point to benchmark your results is AD-Bench. AD-Bench is a collection of 57 benchmark data sets that have been curated and annotated, and they come from pretty much all industries, and they have been published together with the library PyOD. More about it in a minute. You have the algorithms, you have the data. How should you evaluate these results? The first point is that there are different dimensions you should consider. First and foremost, you should care about the correctness of your algorithm, of course. You are in the unsupervised setting. If you do have a few labeled samples, it's best to put them in the test set, and then you should use the performance metrics that are related to extreme class imbalance, because anomalies are rare. So in this case, you should compute AUC, F1 score, precision, recall. If you don't have any samples at all to compute model correctness, then you can check anomaly injection. Anomaly injection is a technique of artificially creating anomalies, inserting them, injecting them in your data set, and then using these samples in order to compute a measure of model correctness. The next point is model size. This is going to influence the prediction speed, especially if you are in the streaming scenario or in real time. You also want to have a very fast response time. And lastly, model stability. Model stability across runs. This also tells a lot about how reliable your algorithm can be. Point adjustment is a method that is commonly used in scientific papers, and it consists of further tuning the detection thresholds over a rolling window in order to be able to detect subtle anomalies. However, there is also a lot of criticism about this method, but most of scientific publications still use it because it provides a significant boost to the scores that are being reported. And I think it's important for you to know that this method exists, it can be applied, and it has these interesting side effects. Okay, we are at Europython, and I described a number of approaches. Now, let's see what libraries you can use in order to perform anomaly detection today. I grouped these existing libraries into 6 categories based on different focus or perspective you can consider while handling anomaly detection. In the first category, we can always start with good old sklearn. It comes with most algorithms that I already mentioned in the first section implemented, including isolation forest, the clustering methods. However, my favorite go-to Python library is PyOD. Why is that? Well, it comes with 50 algorithms for anomaly detection on tabular data. It has a tremendous collection of contributions, and it also contains extensions if you work with time series data, if you work with graph data, or if you work with big data in a scalable way. In the second category of approaches, you want to focus on the time series nature of your data. And as you can imagine, this means checking methods that perform time series forecasting or reconstruction. While there are numerous Python libraries working with time series data, most of them focus on univariate data or analyzing a single time series. But if you have multiple time series that you want to analyze at the same time, you are in the multivariate case, I suggest checking out the library Darts. It supports multivariate forecasting, and it brings 40 forecasting algorithms, including very recent contributions. An alternative approach, if you work with time series data, is feature engineering. It's a bit like cheating. It's using an approach to extract from your time series data features about the temporal evolution and transform your time series data into a tabular data set. For example, you can check tsfresh, which, given as input a time series data, is able to produce up to 1,200 features that represent the nature, the temporal nature of the time series data. For example, information about seasonality, about trend, about stationarity, pretty much everything. And why should you consider this? Because in this case, you would transform your time series dataset into a tabular dataset, and this opens the door to use the multitude of research and methods that have been created for tabular data. This library also provides functionalities for missing data imputation and different transformations. In the third setting, you want to fix anomaly detection, but in the case of real time. You have to handle also huge amounts of data coming at a very high speed, having limited memory. So in this case, what you should consider is moving from an approach where you would have a precise solution, but slow, to an approximate solution, where you would leverage, for example, only summaries of the data or sketches. And as you can imagine, this also brings its own algorithms for streaming. My favorite algorithms for anomaly detection in the streaming setting are lightweight online detector and Xstream. They function in a similar way by first reducing the dimensionality of the data using, for example, a random projection, and then applying a technique to identify anomalies. If you are in the streaming setting, I suggest checking out the library PySAD, streaming anomaly detection. This comes with 16 algorithms for anomaly detection dedicated to streaming, as well as ensemblers. Ensemblers offer you the possibility to put together the results of more algorithms into a single prediction. In this approach, we want to look at the shotgun solution, AutoML. Instead of checking out different libraries, maybe we want to throw an AutoML capability at it. I recommend checking out the package called PyCaret because it has an extension dedicated to anomaly detection where you can leverage 12 algorithms and see which one works best on your dataset. Most of them work with tabular data. If you have other kinds of data, you can use a method to transform it into tabular data, and then you can use any one of them. But in this case, nothing prevents you from using also hyperparameter optimization on the set of algorithms that you like best. In this approach, not only that you want to do anomaly detection, but you want to deploy the latest and greatest, the cutting edge contributions that usually make it first to conferences. But in that case, they have implementations in private GitHub repos, which are not very well maintained, and thus it's quite risky to adopt them in the industry. The very good news is that there's this library in Python, DeepOD, that did a fantastic job of publishing 27 algorithms that have been presented at conferences over the last 2 years. And as you can see, they did an amazing job of hiding the typical complexity of research repositories under very clean interfaces. And lastly, LLMs. As you know, this topic is hype today. A survey cited here asked the question, can we leverage zero-shot LLMs in order to perform anomaly detection? And they checked 2 approaches, prompt engineering and forecasting. They tried it on 11 data sets, and the experimental results indicate that they underperform by 30% traditional state-of-the-art, which is not to be surprised about, because even if LLMs have this multitasking capability, they were not designed for the task of anomaly detection. And they can't be very good at this job. However, if you have your data set, you can still perform fine-tuning, but this would come with a significant investment. Finally, we looked at different approaches, a variety of ways to crack anomaly detection. The last piece of the puzzle is why did they happen and what can we do about them? Root cause analysis. There is a plethora of libraries out there, but most of them perform cross-correlation between input features and the predicted anomaly status. However, we all know that correlation is not causation. If you're interested in true causal analysis, I recommend checking out the library DoWhy. DoWhy provides you the possibility to even measure causal effects to play what-if scenarios, but it also requires you to create a causal graph as input. And very often, you don't know how to create this causal graph on a given data set. In this case, you can check causal discovery. Causal discovery is a method that, in an observational way, would create this causal graph from the data that was already gathered. So in this case, you can check the library causal learn. To conclude, anomaly detection is a topic of underestimated complexity at all phases in the life cycle of machine learning models. While there are numerous approaches, Python libraries, algorithms, there is still no silver bullet because each dataset has its own specificities. To address this gap, I created a GitHub repo where you can just plug in your dataset and see, at least from the methods that I presented today, which one works best for you. However, bear in mind that this will only be the beginning of your journey in the treacherous world of anomaly detection. I would like to thank Kiwi for supporting me in delivering this presentation. If you're interested in other tech content, please check the QR code. Also, very good news, we are hiring Pythonistas, so feel free to come and chat with us at our booth. If you have any questions about anomaly detection or any other machine learning question, I am here, so you can ask me now or feel free to drop me an email to add me on LinkedIn. Thank you.
Thank you very much. So we are almost out of time, but we'll take one very quick question, just one question.
Okay, then everything was crystal clear.
Thank you.